Hello and welcome to this Defense IQ webinar on why does ecological transition matter for military vehicle manufacturers. My name is Tiago Machado, Content Manager here at Defense IQ. I am today with some experts, Jean-Luc Chabidet, Director of Research and Innovation at Capgemini Engineering, Etienne Chave, Innovation Leader of Energy and User Experience at Arquus, and Bernard Tonon, Program Manager of Energy Systems and Networks at CEA, are our esteemed presenters. Moderating the conversation will be Sophie Wierskin-Thiron, Industry Vice President of Space, Defense, and Naval at Capgemini Engineering. If any of our attendees have any questions, please feel free to write it into the question box or email us at engineering@capgemini.com. That is engineering@capgemini.com. And we will try to answer them in the Q&A section or get back to you by email if time runs out. Over to Sophie Wierskin-Thiron.
Hello everyone, thank you for joining and welcome to today's webinar on why does the ecological transition matter for military vehicle manufacturer. I am Sophie Wierskin-Thiron, Capgemini Engineering Vice President, Space, Defense and Naval, and will be your moderator for today. In today's webinar, we have on the agenda eco-mobility and hydrogen with Jean-Luc Chabidet. How does Arquus intend to answer to this ecological transition with Etienne Chave towards energy autonomy for military camp using new energy technology and advanced energy management tools with Bernard Tonon? When energy is at the heart of the future of our society and economy, the forces have to prepare themselves and be ahead on energy transition. So please join us for what should be an incredibly lively conversation, starting with our R&I Director of the Future of Energy, Jean-Luc Chabidet of Capgemini Engineering. Jean-Luc, the floor is yours and have fun, all of you.
Hello, everybody. I'm going to say good morning, good evening. I'm very excited to be there with you today to share some kind of interesting message. I hope interesting messages. So I'm working for Capgemini Engineering. I'm belonging to the Group R&I organization, and I'm in charge of Future of Energy program that aims to cover the whole value chain from energy production, distribution, storage, and usage, with a specific focus on hydrogen and talking about usages, a specific focus on mobility and any kind of mobility, any kind of vehicles. Next slide, please. So, two main topics. First of all, what's going on within the different markets in terms of eco-mobility, and after that, we'll elaborate a little bit on hydrogen, what's going new inside of story, which is a little bit old, and we'll come back later on that. So, what's happening on the naval, aerospace, aeronautics, railways, and commercial vehicles? What are the common trends that we can identify when thinking about eco-mobility? Next slide, please. So 4 major trends. First of all, the move towards more and more autonomous systems, autonomous vehicles, sometimes fully autonomous, sometimes not that fully autonomous, but this is definitively a path forward in which all the mobility markets are going on. Second trend, the booming of new way of transporting people, eventually goods. I'm talking about drones, I'm talking about a taxi, eVTOL, I'm talking about light trains to serve remote areas. So there are some new kind of transportation means that are appearing as part of this eco-mobility fighting, for sure. The third one is the environment constraints in the electrification. So, and we'll come back a little bit later on that. So to face the global warming, there is a fierce battlefield against CO2 emissions. And transport is one source of this emission, not the only one, but one source. So definitely there is a battlefield to reduce the CO2 emissions. And the first way to go forward is to use electrification. Okay. But, and you'll heard this word several times during my presentation, effectiveness in terms of engineering how the system works and what the cost of it. So TCO, total cost of ownership, is key. So effectiveness is at any stage of the rocket. And the fourth trend is digitalization. All those value chains have to be aligned, have to be anchored, and those domains are massively producing data. And so there are huge challenges and huge opportunities to generate valorization on existing data. But we are facing some issues around IP conflicts and so on. So these are the four trends that we can identify on ecomobility. Let's move to the hydrogen part. Next slide, please. Sorry. So what's new? I think we missed a slide. Did we miss a slide? Okay, move forward. Okay. Okay, so let's go to the challenge. So we'll go quickly. So I think most of you knows what's the specificities of this little molecule, the tiniest of the universe. It has a very good ratio weight versus energy, but very bad in terms of volume. It leaks very easily. It's very corrosive. And to use green hydrogen, which is the objective, you need to have a huge amount of electricity when talking about some electrolysis production technology. And again, there are challenges on the whole value chain to produce, to distribute, and store the hydrogen. And we'll see afterwards, and we'll discuss a lot about this notion of hub. Market reactions, different kind of reactions depending on the market. In aviation, these are the most fierce challenges to face because of safety, because of the constraints of the volume that needs that leads to use a liquid form of hydrogen with thermal and cryogenic issues. So definitely aviation is the most challenging market for hydrogen. The rail, at the opposite, is the what appears to be the most simple because any diesel train is already electrified, and volume and weight is not that challenging as in aircraft. And we have at the moment some existing and operating solution on that. Automotive. This is probably the market where the social demand is the most important. The first step is to go to BEV, battery electrical vehicles. But we'll see afterwards, this does not really fit with some usage, and notably when talking about a heavy kind of mobility. Naval is silently booming. This is a market that will emit the biggest quantities of CO2 on the next years to come. And this is also a market where challenges are very important, and hydrogen might take a role on that. Next slide, please. So hydrogen is an old story. Next slide. Okay, so just a slide to illustrate what's going on at the moment. So which countries are producing hydrogen, but which kind of hydrogen are we talking about? We're talking about hydrogen produced thanks to SMR, steam methane reformation, on gas or eventually coal. It works well. Technology is very well mature, but it produces a huge amount of CO2. So no way to reduce CO2 emission on usage when you are producing a lot on the hydrogen production. Next slide, please. Fuel cell. So hydrogen is something which is massively used for decades in the heavy industry. The same for fuel cell. The first fuel cell has been invented in 1839. So nothing new there. The technology are there and the bricks are there. So what is the challenge and what are the opportunities? Next slide. Okay. What's new is the fact that first we are trying to tackle the CO2 global warming, and we are looking for ways to have mobility which is less and much less CO2 producer. So green hydrogen is a solution. So what's green hydrogen? Green hydrogen is hydrogen made of water electrolysis that requires a huge amount of energy but produces no CO2. So very interesting in terms of zero carbon footprints, very good social acceptance, but the cost is quite, at the moment, expensive. The gray hydrogen is absolutely the opposite. It generates a huge amount of carbon. The production costs are quite low. Social acceptance is not that good neither. And in the middle, we have blue. So as you know, blue is gray hydrogen produced thanks to SMR. But the CO2 is not, CO2 which is produced is not released. It's captured using CCUS techniques. So what's new is different ways of producing hydrogen. Next slide, please. What's new is the hydrogen value chain. When thinking about other usages than pure heavy industry, we face some challenges on distribution, and we'll come back, I think, a lot during this webinar. So we can use pipelines, eventually blended, hydrogen blended with natural gas, or we can use pipelines just transporting pure hydrogen, or we can use the boats, the trains, the trucks, and so on. And we can use gaseous form, liquid form, eventually solid form. This is something different. And the utilization, the use cases are much more numerous nowadays than 20 or 30 years before. So what's new is the place of the hydrogen inside mobility, and wider than that, lots of different use cases. Next slide. So going quickly on that, so we know that transportation emits around 25% of the global CO2. Okay, 25 is, we can say it's not that big, but yeah, it's a challenge to be tackled. And again, depending the markets, the CO2 volumes are really not the same. Automotive, aviation, naval, and rail. Move to the next slide, please. Okay, first reaction of from political perspective, we need to go this way. So we need to help the stakeholders. We need to help the industrial to face and tackle the challenges. One way to do that is to provide subsidies and money on the table. So it's valid for the US, for France, for Germany, for Italy, for Europe. And Europe built a very straightforward roadmap and action plan, very prescriptive, and there are lots of information that are accessible. Next slide, please. Second reaction is from the market perspective, the fact that the stakeholders want to collaborate and very closely collaborate to be more efficient. Effectiveness, again, is the key word on this global hydrogen challenge. So you have lots of collaborations between sometimes competitors, sometimes energy producers, distributors, users, tier ones, OEMs, and so on. Lots of people are trying to collaborate to go faster and to save time and money to achieve the target. Can we go next slide? Okay, so quickly, the Capgemini value proposition. Next slide. So for our vision is to help our customer to tackle TCO, total cost of ownership, on two directions: pure engineering and economical, take into account the operations of their system. So to do that, we think we need to cover the whole value chain from the energy production, eventually renewable energy, to produce green hydrogen, the operators of the fleet, and we'll come back later when talking about defense, the fuel cells, the equipments, and all the equipments that are present on the value chain. So again, the key is total cost of ownership. Nowadays, we have said before, lots of subsidies, but this is not really the real world. So subsidies won't be there for 20 or 30 years, and we need to tackle the competition that will come from China. This is something crystal clear. So our value relies on three dimensions. First of all, the engineering and system engineering on any parts of this value chain. The hydrogen expertise that we have, notably coming from research and innovation, and intensive use of digital accelerators. Next slide, please. So again, a slide, some logos, not exhaustive, but again, illustrating the fact that we are there, we are present, we are working with any customer on the whole value chain. So what we're building is engineering, all the key disciplines: thermal, cryogenics, safety, electrification, and so on. We need hydrogen expertise, notably, as I said before, from the RNI dimension, and some accelerators that could be summarized onto simulation plus plus, going up to digital twins sometimes, and artificial intelligence-based assets that helps to predict the cost of the energy, predict the maintenance, predict different kind of challenges that can ease and tackle the CO2 and the TCO objectives. Next slide, please. Okay, another way to illustrate that any part of this global value chain is to be simulated. This is the situation today. And again, a huge amount of data to be produced. Sometimes there's some IP conflict, but we are an independent and I think pertinent company. So this is a very interesting situation for us to help our customer. Next slide, please. So yeah, just a slide to illustrate the galaxy of some of our research and innovation projects that are related to hydrogen, again, to cover the whole value chain, production, storage, supply, and some applications. Next slide. So I'm going fast because of the time, but all this information will be accessible on the web after the webinar. So some use cases quite interesting, I think. Next slide. We do have the capability for a long time now to help the customer to integrate fuel cells inside different kind of environment, from telecom station to a tram, a bus, a train, or eventually a bus. And we also have capability to manufacture, to build hydrogen test benches. So we know what are the challenges to integrate fuel cell inside vehicles. Next slide, please. This is another very interesting project, quite confidential, so I won't name the clients, but let's say that it's a worldwide fuel cell provider that sold his fuel cell to a bus OEMs, that sold the bus to a bus operator. And what's happened? Every day at night, the driver coming back to the garage, store data into a black box that's going to a private cloud from belonging to to our customer. And so we have a huge amount of data to play with and to generate some valorization. And so did we. We use 6 years of recording for 2 years, sorry, of recording for a fleet of 6 buses, and we help the customer to understand what happens in terms of effectiveness, to predict the failure of the equipment. And nowadays, we are going to run this analysis not only in the cloud, but very close to the fuel cell. Interesting roadmap and very exciting projects. And last but not least, in terms of illustration, next slide, please. Yes. So as you can see, we're not talking about a train, a bus. We're talking about a naval market. In fact, the picture is not really in accordance with the project, again, confidential. We're not talking about something which is floating, but something which is an object which is going under the surface, under the water. We're talking about submarine. And what do we did there? We help the customer to integrate the whole hydrogen system inside a submarine. And there the system is composed of reforming of methanol to generate hydrogen, to power a fuel cell, to power an electrical engine. And so we face 2 kinds of challenges. First of all, pure engineering, as I said before, thermal, safety, electrification, safety, and so on, and the safety compliance and the safety certification. So we have the customer on two dimensions: the pure safety for the prototype to be certified, and from engineering perspective to integrate and make the system work inside a very confined environment. This is it for me. I would be happy to answer any question that will be coming afterwards, after the session, or eventually after the webinar. Thanks a lot.
Jean-Luc has drawn an overview of the different usages of hydrogen in various applications. And now Etienne will explain on the military side how Arquus intends to answer to this ecological transition. Etienne.
Hello, everyone. Happy to be there today with great speaker and great audience. I belong to Arquus Defense, French military vehicle manufacturer, and I'm leading energy subject. So why ecological transition matter for industry vehicles manufacturers? Jean-Luc gave a first answer. Military vehicles manufacturers should follow eco-mobility trend because their components highly rely on commercial vehicle components. The second aspect is that military vehicles, when used in training mode, should comply with legal emission rules. And the last concern is fuel logistics, that is critical on battlefield, and Bernard Tonon will provide data on this topic at the end. So I will now explain how Arquus intend to answer this ecological transition. Next slide, please. So for Arquus, being a business unit of Volvo Group provides reliable solution to develop its strategy. The Volvo Group is determined to fulfill its commitment to the goal of Paris Agreement. Volvo set a clear target with STBI certified method. So in 2040, 100% of products shall be fossil-free. In 2050, Volvo Group shall be neutral carbon. Arquus can rely on Volvo solution to upgrade its product. So biofuel, electrification, energy efficiency, and hydrogen-based solution are the solution from Volvo we can rely on. Volvo Group and Arquus are also considering environmental production footprint by limiting substance of concern and studying recyclability. Next slide, please. So biofuel is the first step of Arquus strategy to contribute to CO2 emission reduction. We can achieve up to 90% of CO2 reduction from fuel extraction to wheel. 100% today, 100% of Arquus truck engine are compatible with biofuel. So we can already apply this solution today. Of course, e-fuel could also be a player in the future with advantage of keeping thermal engine and also NOx reduction, which is possible with this type of e-fuel. Next slide, please. So the second step is hybridization. Arquus believes hybrid driveline is the good answer to reduce fuel consumption. First of all, we cannot go to 100% electric vehicles. It is not achievable because even with optimistic roadmap on a battery, we would have to replace the 400-liter fuel tank by a battery with weight. The weight is multiplied by 22, and the volume is multiplied by 11. So Arquus has already several experiences on hybrid vehicle. We have a VAB Electer project where we achieve 15% fuel saving. We have also Scarabée vehicle, you saw in the video at the beginning, which is natively equipped with a hybrid driveline. Based on simulation, we think we could achieve, for instance, on Griffon vehicle, we could achieve 41% fuel saving. Of course, this is because there is a high standstill rate on this vehicle. That's why we can achieve such figure. So next step for us should be to build a demonstrator of Griffon hybrid with French Army and confirm this data. Also, we are studying hybridization of battle tank with French school Ensta Bretagne. Because we think also we have high fuel saving reduction on the battle tank. Also, hybrid driveline provide other key advantages for combat vehicle. We have increased silent watch, allowing usage of air conditioning at standstill, for example, and high energy battle weapons and system. We have also increased power production, meeting future need and replacing EV generator on camp. Last, we have also 100% electric mode possible, meaning silent approach and also fast move due to electric and motor, which can be used for missile avoidance, for example. At last, Arquus is working with Paris-Saclay University to develop energy optimization algorithm adapted to military scenario. And Arquus is also a member of MILVA NATO group to promote high voltage standardization. Next slide, please. So hydrogen on battlefield is raising several challenges. Jean-Luc speak a lot about this, but I would summarize. Compact storage, safe storage, air filtering and cooling for fuel cell is a challenge. So replacing fuel with hydrogen would lead to multiply by approximately 5 volume and weight of current tank. But of course, for hydrogen, Arquus can rely on Volvo Group technology. We have a hydrogen combustion engine with existing prototype today. And of course, we have also fuel cell developed by a joint venture between Daimler and Volvo. Also, Arquus believe dual fuel technology could be a solution because we would be able to rely on fuel on battlefield and hydrogen when vehicle is in training. For storage, Arquus is working with several partners to develop a safe storage approach. And at last, Arquus is preparing calls to build demonstrator applying this technology to make sure hydrogen is a viable solution for military vehicles. So thank you very much for listening to me, and I'll give the floor back. Thank you.
Thank you, Etienne. After the military vehicle, our last speaker, Bernard Tenon from CEA, the French government-funded research organization on energy, will present the following topic of new energy technology for military autonomous camps and advanced energy management tools. I let Bernard now speak further on this subject.
Thank you, and hello everyone. Thank you for the presentation. The goal of my talk here is really to try to do the links between the previous presentation and try to do what is going to occur at the camp level. So the objective in the future, we believe that we need to have some evolution of the camp and not to rely only on fossil fuel, which is provided by trucks to the camp, and to find into a new way of operating the camps. Next slide, please. So the first thing that we are going to work to consider forward operating bases, which could be permanent or semi-permanent bases, with some hundreds to some thousands of persons on site, but also some special forces operation bases, which have much short time. The present situation for producing the energy at the camp level is relying on diesel genset, and they are using the conventional, the unique fuel, which is provided by the camp. And the first thing we have to know is, in terms of figures about today, most of the fuel which is transported to the camp is used to generate electricity. About 30% is used for the vehicles, and 70% of the fuel is used to generate electricity. And the second point also is bringing fuel to the camp is consuming fuel also, because you have to, all the logistic chain is very complex, it's very heavy, and it relies on several constraints. And we assume today that 4 liters of fuel is consumed to transport 1 liter to the camp. So this is not very efficient. The second point also, it's today the cost of the fuel in operation can be up to more than 100 euros or dollar, if you want, per liter, which is much more that we have the cost that you can find in the civil car. The one other part also is logistic. Logistic is one of the key of the system. There are some tens or hundreds of trucks which are coming monthly or weekly to the camp, bringing the fuel to the camp, and this is a weak point of the system. And it has been from some studies recording what have been camp in Afghanistan, for instance. It is assumed that one attack over 24 convoy have been measured. So that is quite important. We've seen that 4% of the trucks are attacks, which are a very high number. And this also implies that some soldiers are killed or wounded during the survey. So the first thing that we have to keep in mind that from the military perspective, the major driver at the camp level is not the cost of energy, is not the CO2 emission, it is logistic, because logistic is the weak point of the camp. So we have only to think on the military side. Yes, of course, environmental constraints are important, but they have to keep the operational capacity, and logistic is the weak point of the camp. So now is how can we develop solution to reduce this logistic constraint? So next slide, please. So first at the camp, what we think that in the future, we need to reduce the energy dependence of the camp from the logistic and try to reduce by, and we assume it is possible to reduce by 30 to 50% the logistic at the camp level. This by two major means. The first one is energy efficiency. So reduce the energy consumption by using more efficient system, by recovering energy. I will give you some example. And the second point, to produce locally energy at the campsite. So now we have to try to have a global approach of the system, try to see from the civil technology what could be used and transport from the civil area to the military area. What type of power sources are available at the camp level? Can we use solar energy? Can we use wind energy? Can we use eventually hydropower, geothermal power? Can we also transfer the waste which are generated at the camp as energy sources? And what is the energy which could be generated by heat of these sources? Then we have also to optimize or to maximize all the power conversion system, heat to power, power to energy, heat to cold. All this conversion system has to use the more advanced system in order to reduce the energy consumption. As we will rely on renewable sources or sources of energy which are being with fluctuations, and as the usage also again to fluctuate during time, we need to have some storage capacities at the camp level. So we need to be able to store electricity with different means, whatever the solution which is used. We'd also probably to have to store heat or cold in order to avoid peak energy consumption. And also we have to store hydrogen at the camp level. The next point which is important is logistic. How we're going to transport this energy to the camp. We need to transport the remaining fuel, which whatever it can be biofuel, it can be e-fuel, it can be hydrogen, but we need to transport it to the camp. It can be transported by road, it can be transported by rail, it can be transported by air, but we have also to take into account the CO2 impact of the transport during the optimization. One important part is also the distribution. We need to develop energy networks at the camp level in order to distribute energy, heat, electricity, cold, and electricity to the different user. And finally, all this system has to be controlled, managed, and optimized. And the last one is we are in a military environment, we need to guarantee the safety, we need to guarantee the security, and all this system should be interoperable and also modular. And the last point, of course, as has been mentioned, we don't know what would be exactly the camp location. It could be in any region of the world. It can be hot region, cold region, tropical conditions. So this has all the constraints that we have to face. Next slide, please. So the first thing is we need to change the way that we are going to manage energy at the camp level. Today, it is only we are providing electricity, we have diesel gensets which are provided on site, and we need to shift to a more modern way of operating the energy at the camp level with local microgrids, which are implemented at some part of the camp when you have some local production, when you have some local management of the system. And all these microgrids are going to be connected between them and synchronized through a central control system. This type of way to operate a camp provide a higher reliability and a higher, let's say, flexibility, or say, at the design level. Then this is how we have to design in the future the camp level, not only a very centralized, but we have something between centralized system and also some autonomy subsystems. Next slide, please. In the next slide, I try to give you some examples on how we can have energy efficient systems in order to reduce the fuel consumption for the needs. One of the major consumption of the camp level today is cooling when you're operating in cold region, or heating when you're operating in cooling when you're operating in hot region, and cooling and heating when you're operating in a cold region. With this one of the most important part of the consumption is air conditioning and refrigeration. And today we are using electricity, which is provided by the diesel genset, we're using this electricity to produce cold, heat, and usage. As you know, a diesel genset is not a very efficient system. Only 1/3 of the energy is converted of the fuel, which is being consumed into the genset, produced electricity. The 2 other thirds are waste energy to heat. And the principle is try to convert this heat into valuable energy. We can transform heat to cold using absorption technology, and we can, for instance, generate 50 kilowatt from 100 of kilowatt of waste heat. We can generate 50 kilowatt of cold, directly substituting this cold to electricity. And we can also, for instance, also try to use this heat available to desalinated water to produce energy directly for water. Or we can hook directly the heat for sanitary hot water or heating the different usage, rather than using electric resistance. Next slide, please. Another also options at the camp level. Today at the camp, there are also a relatively large amount of waste which is generated every day. We estimate that 2 or 4 kilograms of waste are generated per day and per person. This waste can be solid waste, for instance, from bottles, from system which also all at the camp level, but also we have some organic waste coming from the food. And all this, the food waste can be converted by biomethane. So we have to develop micro-methanization systems, and the solid waste also can be converted to syngas or pyrolysis systems. And what we assume today that if only 50% of these waste are recovered, we can produce an equivalent of liter of fuels, and this can represent something about 3 to 5% of the energy which is consumed at the camp level. 3 or 5% is not very important, but it's not negligible. And we always have to think as 5% of energy reduction is 5% less of logistic. Then it is less convoy which is attacked and more operational efficiency. We always to think about impact of energy efficient measure into logistic. Next slide, please. So now coming back to the link with vehicles. As it has been mentioned, in the future, we'll have hybrid vehicles. You'd have vehicles which will rely on hybrid vehicle with electricity or usage of hydrogen in vehicles. Concerning electric vehicles, today the vehicles will have a certain capacity into the batteries, and in order to avoid consuming fossil fuel, it is better to try to recharge the batteries when they are in the store in the parking slot during parking of the vehicles. And we try, if it is possible, to recharge these batteries using renewable energy. For instance, we can use PV shaders. This is already developed and implemented into the civil application. And we know that we want advanced manager energy management systems almost charge with 80% with solar energy the vehicles if you have an advanced management systems. The second thing which is quite important also is, as the vehicles will be on site and they are not always in operation, you can use the batteries of the vehicles. You can use also the capacity of the generation of the vehicle to generate electricity to the camp. It can be used as a storage capacity at the camp level. It can also be used as a backward system for regenerating electricity in case of losses of capacity. So we really need to have a global view, and vehicle will be a user of energy, but it could also be a provider of energy and provider of storage capacity. The last part also is about hydrogen. we have to think about how can we use hydrogen into vehicles. This can be presented before, but now how do we produce, or where is the hydrogen coming from? It can be either produced locally at the camp level using electrolyzer, but then we have to develop efficient and very robust system of electrolyzer, or it can be transported from outside. And then the important part is which means that you can transport it: compressed hydrogen, liquid version, or liquefied hydrogen. All the option has to be considered, but it is a very important part to see how can we transport hydrogen to the camp level. Next slide, please. At the end, now we have developed several technologies and options. We now have to change to an integrated approach of the design and the operation. First, we need really to analyze what will be the fusion needs at the camp level. So instead, what will be the needs for electricity, what will be the needs for the camps, what will be the camp, the size of the camp, what will be the needs for the vehicles, what type of vehicles we have, heavy vehicle, hybrid vehicles. And for this, we're going to define the energy needs for all the different vectors. Then through some simulation tools or energy planning systems, we are going to define the energy systems, what type of energy production we need, what type of energy storage capacity we need, try to develop the business system, develop the control afterward. Then we have to validate and check if the system is efficient during either real simulation, experimentation, or in a simulated environment using digital twin to validate the reliability of the design and the robustness of the design. And of course, after it, you can transfer it to the field application. And then we have to have some online control and monitoring and predictive maintenance and to maintain the operational capacity of the system. Last slide, please. Just now to summarize, as we are a research and technological organization. We are about 1,000 persons working in different fields of area technology, and we are here to support companies, either technology providers, engineering companies, or end users, in different area. And we are active in renewable energy production, mainly on photovoltaics. We're also working on storage and flexible solution. We're working on batteries and hydrogen vectors, where we have some specific technology. We are developing batteries, we are developing electrolyzers and fuel cells. And also we are working on system efficiency. And the last point, we are also working on circular economy, and also to take into account how to manufacture the component, how to manufacture the fuels, how to manufacture the components. Because also it's a part of the system is to ensure the security when you have to ensure that you have access to the resource to manufacture not only the fuel, but also the system that will be on board and used at the camp level. Thank you for attention. I will again now back the floor to the moderator.
Of course, energy, the subject is so big, so huge, so interesting. With Jean-Luc, Etienne, and Bernard, we have done an overview of energy management from 3 different angles: engineering, industry manufacturing, and French government research that show you the possible evolution of energy management in the field. Thank you for joining us. And now back to Thiago for the Q&A session. Thank you.
Thank you. Please remember to type your questions into the webinar question box or email us at engineering@capgemini.com. First question goes to Jean-Luc Chabardier. What differences in mission profiles of commercial and military vehicle can affect the duality of onboard hydrogen system solutions?
So I was saying that it's a very interesting question, but before going to the answer, which is to focus on the what affects the duality of the solutions, let's take 10 seconds to talk about the similarities. What are some similarities between commercial usage of hydrogen and the defense kind of activity? Is first of all notion of captive fleet, which is very, very, very connected to this the hydrogen distribution challenges. Okay, for many reasons, hydrogen distribution is quite tricky to organize, and the market is going to hubs that are serving different kind of mobilities, and definitively commercial vehicles like taxi, trains, or eventually aircraft and military vehicle are to be considered as captive fleet, gathering at the same place at a given time and to optimize the hydrogen distribution process. Second similarity is the appetite of solutions which are not relying on BEV, which is battery electrical vehicle, because we know that out of the main concern of power and energy and so on, there are some operation constraints on autonomy and time to refill that are affecting both sides, commercial side as well as the military side. And again, this is the appetite and that has been presented by Etienne on this very pragmatic solution on using hydrogen onto thermal engines and not only electrical ones. The answer, what's affecting, in fact, the duality? It's question of effectiveness. It works, but is it efficient? Inside the vehicle, when going onto details, the way the vehicle is operated, and specifically the military vehicle is operated, this vehicle has to climb onto hills. So inclination has to be taken into account. And maybe you know, maybe not, but if you are using the PEM, the membrane technology for the fuel cells, with a high inclination, you can drown the fuel cell. Why? Because the fuel cell is producing water, and water, if it's not moved away, it will affect the effectiveness of the chemistry which is inside the fuel cell. So inclination is not that good for most of the PEM fuel cells. You also have the external environmental constraints. I'm talking about the temperature, either high temperature when talking about desert or very, very cold temperature. And this factor affects the effectiveness of the global hydrogen system inside the vehicle. And definitely those constraints we can understand, are much more present when talking about military vehicle rather than commercial ones. And there is another factor that affects the duality, which is again the logistics and the hydrogen distribution. Maybe you have seen that in Europe, the truck market is quite active on using hydrogen, on project to use hydrogen, and there are projects named hydrogen highways, meaning building networks like highways or within the highways where the trucks can refill. These are hubs, I said before, but fixed hubs. Or when talking about military vehicles, definitely you have some camps that are fixed for a while, but some other that are not. And there it raises this question of an agile way to distribute hydrogen. And this is something very, very, very tricky. On the other hand, we have in any army of the world, we have people dealing with logistics, and notably logistics on gasoline, diesel, fuel, and so on. So yeah, so just to summarize, there are some common factors between commercial markets and military vehicles, but there are some other factors dealing with effectiveness that has to be very carefully considered. I hope I answered the question.
Fantastic. We have here a second question for the same speaker, which is a nice follow-up. Is the use of hydrogen as an e-fuel for thermal engines a solution to be taken into account?
Okay, answer is yes. And I think Etienne already mentioned that, as well as Bernard. So why is it to be taken into account? Again, when talking about what's going on the web and so on, the publicity is on hydrogen for electrical vehicle. That's definitely something to be investigated. But we don't have to forget that hydrogen can be used inside thermal engine. We have to consider again, because of effectiveness issues, that the engine has to be adapted and sometimes rebuilt to face some challenges, notably in the thermal dimension, but not only. And also considering that this engine the combustion of hydrogen will produce water, which is okay, but also will produce some NOx, which is really not okay because of the pollution. And Bernard and Etienne mentioned that before. So Arquus is having some technology to reduce, eventually prevent this NOx emission outside the vehicle. So yes, the thermal engine technology is something very mature, and it's very possible there are lots of projects to adapt this technology to hydrogen as a fuel. Second dimension is it is not in opposition with a fuel cell electrical vehicle. Why? Because the engine is not the same, but the challenge to transport hydrogen inside the vehicle is the same. You have to have a tank storing hydrogen as gaseous form and high pressure, 700, maybe 100 bars. So on both kind of solutions, you have a common challenge, which is to transport hydrogen inside the vehicle and eventually refill the hydrogen, which could be a little bit tricky. And last but not least, the reason why it's a very good option to be investigated, it's a very pragmatic roadmap. Again, and Etienne has been elaborating on that. This technology, the ICE, the thermal engine, is very mature, and it's very pragmatic way of thinking to move forward CO2 emission reduction, to start by optimizing technologies we have on shelf. This is not as perfect as a pure green FC fuel cell electrical vehicle. It's not as pure, but it's very, very interesting solution and quite affordable and quite ready to be implemented along with the knowledge we have. I hope this answered the question.
Great. Sticking to the theme of hydrogen, we have the following question for Etienne Chavez. How do you intend to store hydrogen on the battlefield?
Okay, so as Jean-Luc and Bernard explained, hydrogen storage is complex. It's very complex. We think high pressure hydrogen storage is too complex to manage on military camp and also for my part on vehicle. That's why today we are studying with partner hydrogen storage solution called LOHC, liquid organic hydrogen carrier, where hydrogen is coupled with other molecule, leading to safe liquid storage at low pressure and ambient temperature. Both solution, liquid or high pressure, have nearly the same density, so volume and mass, and energy needed for conversion is nearly the same. But the drawback with the liquid hydrogen is that you have to take energy to convert in gaseous form before using it in combustion engine. But we think using, as Bernard explained, thermal engine has a fatal exhaust heat that we could use for this conversion. So I would say we think it's a good way. So we'll see in the future if it's okay. But so that's okay for my part.
Great. The next question is for Bernard Thonon. Energy optimization requires accurate customer data for the production units. How do you intend to have access to the sensible information?
Yes, thank you. Yes, you're right. It is a critical question to have access to data. As you know, if you want to do energy optimization in the civil area, we are exchanging a very large quantity of data, almost on real time, coming from your house, for instance, coming from your car, going to the central provider or distributor of electricity, also to a provider. We are exchanging a huge amount of data. And we have to, this is the way to optimize the system and to control it. If you have to transport this approach to the camp, we first need to have access to data. So we need to monitor systems. It is the first thing. Today, the usage of energy is not monitored at a very high level, but we need to implement it. This is not very difficult. It's very easy to monitor, to install energy measures. The critical part in the military perspective is you have to measure the information, but you also have to exchange information between the user, between the central energy management system, and the energy management system has to send some order to the distributed systems also. So we have lots of information going to be exchanged between different systems. And one of the key part is how to maintain this information is safe. So you need to ensure that you will have a cyber protected network for exchanging information between the different users or producers of energy. And this is the key part of the problem, is really to develop safe networks, probably with some redundancy. And also, if there was a cyber attack, you need also to ensure that your local systems can also self-operate without being piloted by other systems. So there's the major challenge is security and cyber protection.
Fantastic. Still with Bernard. In the future, do you think that the armies will be able to reduce energy consumption of the camps?
I think it is not an option, it is required. But as it's mentioned before, the key driver today for energy at the camp level is not CO2 emission, it's not cost. This is not the problem of the, let's say, of the soldier which is at the battlefield. It is, for him, it is operational. So we need to train the soldiers and the users as how important is energy, why it is important to reduce your energy, why it is important to have some good way to operate system, because you're going to reduce your energy consumption, and therefore you're going to reduce logistic. And if you reduce logistic, you improve the operational capacity of your camp. So this is the first message: train the users. And in parallel, and this is our work as engineering company or researchers or technology providers, we need to provide new and more efficient technology, but we have to go in parallel, both training the users and developing technology. One cannot go with the other one, but of course, the first thing to do is reduce the energy consumption at the camp level. Obviously, this is really the first thing to do, and not only at camp, but also in our own life.
Fantastic. Time is just about up. Our last two questions are for Etienne on the challenges on the transition. How do you intend to manage the end of the combustion engine for military vehicles? And is there a plan for military industrials to face a potential lithium battery raw material shortage?
Well, for the first question, also manage end of combustion engine, for small vehicles lower than 5 tons, we think we will be able to rely for a while on stocks of combustion engine, because military vehicles, we have small volume. And we keep, of course, developing our knowledge on fuel electric driveline to be ready when combustion engine will stop. For bigger vehicles, combustion engine market should survive for vehicle evolving in environment where refueling network is poor. And of course, we said several times about this, but combustion engine could stay longer than planned if using hydrogen or e-fuel as fuel. The second question, so how do we plan to face potential lithium battery raw material shortage? First of all, the context of lithium-ion battery in hybrid military vehicle is different from EV automotive industry. We need power battery rather than energy battery, and cost is of less concern. Therefore, we look at different cells than EV automotive and in less quantity. That's why there is a chance that we will be less exposed to shortage. For short term, to avoid this, the idea is to rely on very popular lithium-ion cell form factor, and to select cell chemistry which is manufactured in several countries. Of course, recycling, which is increasing in this domain, will also be part of the solution. For long term, we would like to rely on chemistry made with abundant raw materials and still high safety, of course. For example, sodium-ion technology, manufactured in France by Tiamat, is a very viable option to consider. Also, there is a promising chemistry, sulfur allyl metal, well known by CEA, that could be also an option. So I think I hope it answered the two questions.
Fantastic. That's all the time we have for today. If we have not answered your questions, we will try to get back to you by email. Remember that any further questions that come to mind we can be reached at engineering@capgemini.com. That is engineering@capgemini.com. I would like to thank our speakers and moderator for what was an incredibly interesting webinar. Thank you very much, and we hope to see you soon.
Thank you.
Thank you.